Hi, I'm Edgar, and I'm a software engineer at Google.
Hi, I'm Becky, and I'm a software engineer at Google. So Edgar, the question I'm going to give you today is, I'm going to give you a collection of numbers, and I need you to take this collection of numbers and find a matching pair that is equal to a sum that I give you as well.
Okay.
So for example, the collection of numbers could be 1, 2, 3, and 9. And the sum that I'm looking for is 8.
Okay.
And then another example, just for another set of numbers, could be a 1, a 2, a 4, and a 4. And then again, the sum that I'm looking for is 8.
So in this case, I guess what I'm trying to figure out is you're looking for a pair of numbers that add up to 8.
Yes.
Right? So in this case, there isn't a pair of numbers that add up to 8.
That is true in
Okay.
this example.
And in this case, it is because the 4 and 4 add up to 8.
Correct.
Okay,
Yes.
so this would be like no, and this is like yes. Okay.
Yes, you ultimately have to tell me if the pair exists.
Okay, so how are these numbers given? Can I assume that they're kind of like in memory, an array or something?
Yeah, they're in memory. You can go with an array. You can also assume that they're ordered in descending order.
Okay. Oh, interesting. Okay. So how about repeating elements? Can I assume that there will be, like for instance here, what if I didn't have that 4? Could I use like the 4 and the 4 to get that 8?
You can't repeat the same element at the same index twice, but certainly the same number may appear twice. Like
Okay.
You just saw in the
Okay,
two
so
fours.
like that would be a yes. How about these numbers? Are they integers or are they floating point or?
You could assume they'll always be integers.
Okay, negatives, positives.
Negatives could happen.
Okay, cool. So, well, the simplest solution, of course, is just comparing every single possible pair. So I could just have 2 for loops, one scanning the whole thing, and then the second one starting from, let's say you have the I loop and then the J loop starting from I plus 1 so that I don't repeat the same value, and just testing all of them if the sum is equal to the target sum. I mean, that's obviously not very efficient, but that would be like a way to solve it.
That would work. It certainly would be time consuming, I think, as far as obstacles is concerned. So is there any kind of example that could be a little bit faster?
Yeah, I think that would be quadratic. So better than quadratic. Well, since it's sorted, so okay, I guess I need to figure out when I have a number, what I'm looking for is if there's another number that sums to 8. So if I have a 1, what I need to figure out is if there's a 7 somewhere in the array. And if that's the case, if it's sorted, then I can just do binary search. I guess if I go here and I binary search for a 7, then I go here and I binary search for a 6, which is the complement of that. And when I go here, I binary search for a 5, and in the end, I just don't do anything. And so in this case, I would solve it like that. So that's a bit better than quadratic. I guess binary search is a log algorithm in a sorted list.
Also a good answer.
Okay.
But still kind of slow.
Okay.
So what if you took a look at, instead of going a binary search, which is unidirectional, what if you started with a pair of numbers to begin with?
Okay.
And then worked your way sort of inward from there.
Let's see. So if okay, let me try to bound this thing. So the largest possible sum, I guess, would be the last 2 values.
That would be the largest possible sum,
and
yes.
The smallest possible sum would be the 2 smallest, right? So anything in between. Okay, so the range of the possible values is that, right? So there's nothing that is probably small. There's nothing that can be smaller than this value.
Right.
There's nothing that can be larger than that value.
And you have somewhere to move from.
That's okay. So if this sum is 10 in this case, it's too large.
Mm-hmm.
So I need to find a smaller sum. So I could just sort of move this one over here. And if that is too small now, then I need to move that one over there. Okay, so I think I can just do it with that in a linear solution. Just moving at each iteration, I either move the high one lower if my pair is too large, and I move my lower higher if my pair is too small. And I end whenever I either find two, like in this case, I either find a pair that adds up to 8, or whenever they cross. So at every point I'm moving one of them, so they would have to at least cross. And I move exactly one, so that means that it's linear. Yeah, so that would be a way of solving that problem.
And how does it make that faster than a binary search?
Okay, so in the binary search case, I was doing log for finding, but I had to repeat that for every element. So that was an n log n solution. In this case, I just need to do that scanning the one time. So it's a linear solution. So that's faster.
Right. Okay. So before, maybe we could get to coding it, but before we do that, maybe you could explain. So you explained it in a non-working example. Maybe you could follow through that same process in a working.
Okay, yeah. So here I would start with this and that, right? So it's 5, it's smaller than 8, so I move this one here. So that's 6, that's smaller than 8, so I go here, and then that's 8, so that's true, and I return.
Excellent.
Yeah, I think that would work.
Okay, so what coding language would you prefer to do this in?
I prefer C++, if that's okay.
C++ works.
Okay.
All right, go for it.
Perfect. Let's see. So, okay. Now I realize that I haven't figured out what I need to return. So, do I want the pair, the indices of the pair, or whether I just found it or not?
So, for the purposes of the example, we'll go with whether you found it or not. But let's say you were going to return the pair. How could that become a problem if there was no pair?
So, I mean, building the pair would be easy, right? So, I would just return the pair. If I didn't find it, then I would need to return some sort of like Boolean. So I guess I could make a data structure that has a Boolean that denotes whether the pair is valid or not. Like, has it been found? So like a bool found, and then a pair values or something like that.
And combine those together. Yeah.
And then this is the thing that you return. I mean, it's not very elegant, but it's workable.
Rather than going with a custom object, maybe we'll just return a Boolean then.
Okay, that makes it a lot easier, yes.
But it's good to know that you thought about what you might have to do if there is no viable result.
Okay, so let's just call it has pair with sum, I guess.
Sure.
And so I'm okay just receiving whatever. I would like to receive it as a vector, say.
Vector's fine, yeah, sure.
And we said ints are fine.
Ints are fine.
This is my data. And then I have an int, which is my sum. Okay, so like I said, I want sort of an int, my low, which is 0. Then my high, which is the data size -1. And then what I'm going to do is, while my low is strictly lower than my high, okay, as soon as they are touching, then I know that I can't guarantee that they're different, so that's where I should stop. Okay, while my low is less than my high, and this also solves the problem of what happens if this is empty, because then if this is empty, this would be a -1, and then that would be violated, so I would never enter and access any of the values, so that's fine. So while low is less than high, I guess if my data at low plus my data at high is the same as my target which is called sum, then I have found it. That's it. That's my pair. And here's where I would construct that pair if I needed to return it. But like you say, for now, I can just return true. Now, if this is larger than sum and this is lower than sum, so I think I'm better than just doing it 3 times. I'm just going to store it in a variable, which is my s. Is that, and then say if s is my sum, then return true.
Okay, I'm going to stop you right there.
Okay.
Excellent solution. I see what you're getting at here, but now I'm going to throw a little wrench into the mix for you.
Oh boy.
I can no longer guarantee for you that the numbers in this collection are sorted.
Okay, so
you have to think of a different way to compare them against each other now.
I mean, if the first thing I do is just sort, of course, then I solve this problem the same way, right? So that would be still an n log n solution.
It would.
Which would be like the same as the binary search as well.
But it's too slow for Google.
Okay, so you want faster than that. Okay. Okay, let's see. So if I go back to this idea, okay, so let me erase this. If I go back to this idea of when I look at a number, what I need to figure out is if the complement is in the rest.
The complement meaning?
The 8 minus this value, right? And in this case, when I have the 1, I need to figure out if 7 is in the rest.
Yes. Okay.
If I cannot sort, and searching that will be linear, so that's not a very good idea. But maybe I can do it the other way around. So I build it up little by little, and instead of just sort of asking a blanket, is there anywhere? I just ask, have I seen it in the past? So for instance, if I'm here, what I need to find out is if I have seen 8 minus 3. Have I seen 5 in the past?
That would work. So you'd have to store 5.
Or I guess it's the same, but I could be storing the complements and I just ask, have I seen 3 as a complement of anything of the things before? Yeah. So like I insert a 7 when I see a 1. Sure. I insert a 6 if I see a 2.
You insert the complement?
And then, yes, I insert the complement, and then when I get here, I ask, is this the complement of anything I have seen in the past? Right. So I can use a data structure that is very good for lookups. Okay. Right? So I can do something like a hash table, which has like a constant time lookup.
Hash table though.
Hash table.
Do you need a key in this case?
I guess I don't need I just need the values, the elements. I don't actually want to store any payload. So yeah, I guess a hash set would be the thing to do. So I hash set all of the complements and then I look for them. I need to be careful though. How am I going to deal with the case of repeated elements? So I don't want to be able to say, oh, I have a 4. Yes, of course I have a 4. I'm done. Right? If I have this, I have a 4, I'd have it, so I'm done. That would be a wrong solution. I guess I need to be careful there. So, okay. So here's an idea. I only look for things, so when I'm here, I only look for things that I have seen before. So as long as I check before I insert things, that should work. And then when I add it here, this one will find that because it's in the previous one. So I think that works. Yeah.
Sounds good. Let's code it.
Okay, very well. So let's see.
Good catch.
So, like I was saying, bool of has a pair with sum with my, can I just like my vector, it's a const vector of and data, and then my int sum. Okay. So I need a hash set. So in C++, that's an unordered set. Of integers still. And I'm going to call it complements. well, I don't want to write complements all the time, so I'm just going to call it comp.
Sounds good.
And say these are the complements. As in whatever I need to get the target sum.
Yep.
And so as I said, I just need to be building it up little by little. So I do a for my int value for each of the values in the data.
Mm-hmm.
I am going to first check and then insert. So if my complement, so I check if I have seen it.
First, yep.
And if I have seen it, so that means if it's not in the end, then that's it. That should be a return true. Because this current element and something that I have seen in the past add up to the sum. So obviously it depends on what I've been inserting, so that's what I'm going to do here. My complements is going to be inserting, I don't remember, I think it's add for an unordered set, but there's something, it's either add or insert or something, yeah. So I add not the value, but the complement, like I said. So I do the sum minus value. I feel like I probably need to go through an example, but anyway, to make sure that this is correct. But I think that's it.
Okay.
Let me go through some examples to make sure.
I'm gonna erase these.
Yes. So, okay. So I have a set. My complements is a set, which starts empty. I'm going to run through both. They're kind of the same at the beginning, so that should be fine. So I have nothing in. I check for my first value, which is a 1. I don't find anything, obviously. And then I add 8 minus 1. So I add a 7 here. Okay, so now I have a 7. Then I go for the next one, 2. I look for whether there's a 2 there. No, there isn't. But if I had had a 6 here, adding the complement would have found a 2. So that would be good. So that makes sense. Okay, the 7, it's not there. So I just add now the 6. And here's where they start to diverge. The next case is I get a 3. Have I seen a 3? No. Well, have I seen the complement of a 3? No. So I just shove in the 3. Nice, that 3 is complement. Good point. Yeah, and then the last one, no, I have not. There's no 9 here, so it would correctly return false.
Right.
Now, what about the other one? The other case, I get a 4. I have not seen the complement of 4, so I put the 4 in.
Okay.
Because it's 8 minus 4 is 4. And then, when I get to this one, I have found it, so I correctly return true.
Value is equal to complement.
Yeah. So the value would be 4. I look here in my complements and I do find it, so I return true. Okay, so that works. What happens with an empty? The empty one should never return true because you don't have a pair, so that's fine. If you have only one thing, you never would compare again, so that's fine. So it seems like that works. There is one issue. This could underflow, so okay, let's not worry about that. So I think this is the right solution. So it's linear because I am doing constant amount of work. The lookup is constant, adding is constant for an ordered set, and I do it for all of the values in the input, so that's linear. And the memory is, I guess, linear as well because the worst case scenario, I have added all of them to the set.
Would you do anything differently here if there were 10 million integers in this collection?
Okay, so let's see. So if the input is large, does it still fit in memory or?
Probably not at this point.
Okay, so if it doesn't fit in memory, what I can do, okay, so is the range of these values limited in some way?
You can assume that they might be, yeah.
Okay. So if my set fits in memory, but my whole input doesn't fit in memory, then I can just sort of process it in chunks, right?
Okay,
I chunk it and I just put it in a set and I accumulate it in a set. If we can do it in parallel, then it's kind of the same thing, right? So now you have multiple computers, each one processing each bit of it, of the input, each one producing a set of complements that this bit has seen, and we just sort of merge them.
I think we have enough computers to be able to.
Yeah, so the merging would be a bit tricky because we want to make sure that, again, we don't sort of look for the thing that we have put in. So I guess as long as each individual computer is testing this in the right order, when we merge them, now we can say, oh, well, those two are correctly. So if I have a 4 in one computer and a 4 in the other computer, when I merge them, I would need to be careful that I reconcile them.
Yeah.
But other than that, I think that would be the only consideration.
Sure. Okay.
Yeah.
Excellent. Great job. All right, so just to recap that interview, I just want to go over a couple of things that you should be aware of when you're interviewing, and some of the things that Edgar did very well. So the first thing that he did was he asked for clarification to the problem. So if you don't fully understand the question, please feel free to ask for clarification or ask to have it repeated. You can write it down. You can write it down verbatim if needs be, whatever you need to do to get a complete understanding of the questions that's being asked. And I think some of his clarification questions were, could they be negative numbers or floating point numbers? And the answer to that really does affect the outcome of his code. So it was really great that he asked that question. Another thing that he did is while he was going through his solution, even before he started writing code down, he thought out loud constantly. Constantly thinking out loud is probably the best thing you can do in the interview, because it gives the interviewee the opportunity to see your thought process and use that to possibly course correct you more towards the question that they were asking, or to feed off of that and ask you more questions that might help you demonstrate your knowledge even further, because you may have said something that they can expand upon. But in the very least, it's going to help you to work that problem out. And there's nothing wrong with working that problem out with somebody else. It always makes 2 minds are better than 1, right? So please think out loud. Another thing that he did really great is he thought through everything before he started writing something down. So we thought about how we were going to do it. We actually went through 2 iterations, right? The first thing, the thing at the top of his mind, wasn't the best solution, and it's not going to be the best solution for anybody. So think through what you want to do, and then you might get challenged by the interviewer to think better, faster, quicker, more efficiently. Think through that solution, and then ultimately when you both feel like you're at a spot where you can code it, then you can start coding it down on the screen or on paper. So that's another great thing to do. Another thing that he did really well that I would encourage everyone to do is to test it in real time. So I gave him 2 example sets here. He had something that he could test with. If your interviewer doesn't give you an example, please make one up. Test your solution. Does it work? Does it vet? And then think about edge cases. Edge cases can be important. So in his case, he thought about if he had an empty collection, and he tested his logic with an empty collection. And it was really nice to see him thinking about those edge cases and bringing them up in the interview. So clarifications, think out loud, talk before you write, and then test your solution.